Welcome to this section of the course where we're going to talk about integration by substitution. I've taught you how to do some basic integrals with the trigonometric functions and mainly with polynomials. How do you integrate x squared, for instance? And there's sort of a canned formula for that. And what you're going to find, as I told you at the beginning of the class, is that pretty quickly you're going to get to do integrals that you're not going to know how to solve, and you need to start to employ tricks, so to speak, in order to solve them. And there's a whole chapter on tricks, and we're going to get into all the different kinds of different ways you can do it. The first trick, so to speak, is called substitution. And the basic theme of this section is, if you don't know how to do an integral, okay, sometimes you can make a certain substitution in order to put the problem into a form that I already know how to solve. So I may give you a problem, and it may look like something you don't know how to do, but with a mathematical wave of your arms, you can transform that problem into a problem I do know how to solve. And when I get the answer to that problem, I'll have the answer to my original problem. That's what we're focusing on. And I think the easiest way to do that is to illustrate it by an example. So let's say you had an integral that was something like the integral of x times x squared minus 1 all raised to the 99th power, integrated of course over dx, because that's the variable that I have here. Okay. Well, obviously I haven't given you any kind of a formula to learn how to integrate an integral like this. I've taught you how to integrate x squared and 1/5 x to the 6th power and stuff like that, the basic kind of integrals. But this is different, and you really can't even expand this because, I mean, something raised to the 99th power, you're going to have 99 different terms in there, and it's going to become a mess. So you technically could do that, but it would just take you forever. So how do you tackle this one? Well, we're going to go through some examples, and it's going to be clear. What I'm going to do is I'm going to transform this integral from, currently we're integrating over the variable x. Okay, we have x here in the integral, and we're integrating over this dx, this differential x. I'm going to transform this integral to integrate over another variable, and the name of the variable doesn't matter, but it typically, historically in calculus, you pick the variable u. Okay, so it's going to be an integral over some function of u, it could be whatever, and instead of dx, we're going to end up with a du. And we're going to integrate this, and we're going to get an answer, and you're going to see that it's going to give you the answer that you're looking for in the end. So the question is, how do I do this transformation? How do I make this problem easier? And the way you do that is, in this case, let's say you take u is equal to x squared minus 1. That's the substitution that we're going to make. So you can see that everything in the parentheses here is going to be equal to u. Now just bear with me, and we're going to do some problems, and you'll see how to do this. The next thing you need to do is, I already told you that we're going to transform this integrand into a variable of u, but we're also going to transform the variable that we're integrating over into a du. And the way you do that is you define what u is. So let's go ahead and define what's du dx. This is the derivative of u with respect to x. It's very simple to do that. We just need to take, this is the same thing as y is equal to x squared. Well, the derivative of y with respect to x is just 2x. Okay, you just take the derivative of the right-hand side. So here it's just u instead of y. It's no different. So in order to find du dx, then you simply take the derivative. So what you have here is 2x. Of course, the derivative of the negative 1 is 0, so I don't even write that. Now, in the original problem, I have a dx, okay? And so I need to solve this relation that I just found for dx. Okay, so let's do this. If I multiply both sides of this equation by dx, what I'll get is du is equal to 2x dx. The only thing I did here is multiply the left side by dx, so then they cancel, and then the right side by dx is what I have over here. And so if I solve this for dx, this is just like solving any equation. You're going to have 1 over 2x times du. So all I did to go from here to here is divide both sides of this equation by 2x, and so you'll have dx equals 1 over 2x times du. really, there's not that much calculus in what we've done so far. We just took the derivative, that's the calculus part, and then here's algebra. All you did was solve for dx. And you can sort of see how du by dx takes the form of a fraction. It's a derivative, but it sort of can behave like a fraction. That's why you can multiply by dx, and so on. So, what I want to do is kind of highlight this, because this is sort of important, and we're going to use that. And I'm going to highlight this. Okay? Those are the two important pieces of information you need to make the problem simpler. You see, in order to transform the integral, you need to define what u is going to be equal to, but you also need to define what dx is going to be equal to, and we did that by taking the derivative of whatever we defined u to be equal to. So you'll see how this is going to be clear here in just a second. Now we can transform the integral as follows. Integral of x, because I haven't done anything yet, times u to the 99th power. All I did was say, well, this stuff in here is equal to u, so I'm going to raise it to the 99th power. And then I have a dx out here, but we've solved for dx, so I multiply by 1 over 2x times du. Now all I did was plug dx into here. So you see, to transform the integral, you just substitute for whatever you defined u and whatever you defined for dx. Now look what happens right away. You can see what happens is that this x cancels with this x. Okay? So they go away. So in the end, what you're going to have is the integral of 1/2 times u to the 99th power times du. Now I have an integral purely in terms of u and an integral in terms of du. So now I can integrate that in terms of u, right? No problem. So what's this going to be? Remember the formula to integrate anything raised to the power of whatever. So what you'll have here is 1/2 over the exponent plus 1, which is going to be 100, 99 plus 1 is 100, times u to the exponent plus 1 gives me this. And don't forget your constant that always has to be added when you do these indefinite integrals. Okay, so what you're going to have in the end is 1 over 200. When you flip this around, you'll see that you get the 2 times 100 gives you 1 over 200. Kind of flip that over and multiply, times u to the 100 plus a constant. Now, you would be tempted to circle this as your answer and say, yes, this is your answer, but if you do that, you're leaving your answer in terms of u, and that's kind of rude because the problem's given to you in terms of x, so you want to kind of convert back, and it's very easy to do that because I've defined what u is equal to. So I just say it's 1 over 200. You put a parentheses and you say x squared minus 1, which is what I've defined u to be, to the power of 100 plus a constant, and this is what you circle as your answer. Okay? You see, it's not that many steps. It's not crazy as far as being complicated, but it is very important that you understand what you're doing here. You have an integral. You have to pick something in the integrand to set u equal to. Now, I know from experience what to choose, okay? And you're going to have to gain that experience by working the problems. There's no substitute for that. As we work problems together, I think you'll start to get a sense of what to choose u. But if you choose the wrong u, it's not going to work. The reason it's not going to work is look at what we did here. We chose this as u, we took the derivative of it, and we solved for dx because we need to plug in for dx and plug in for u. When we did that, this dx turned out to give me a 1 over 2x here when we did this and we solved for this. That is what made this problem solvable, because we had an x out here, and then when we did this, we had an x down there, and they canceled. And that cancellation is what allowed us to write this integral purely in terms of u, which let us integrate it. You can't integrate something like this. Okay, you just can't do that. You can't integrate something over u and have an x hanging out there. It doesn't work that way. You can't. If you're going to integrate something, it has to be purely a function of u, like this or something like this. So the only way this substitution business is going to help you in the least is if, in the end, when you plug it back in, you get some cancellation that helps you out. And like I said, from experience, I know what to choose, and the reason that I can look at a problem now, because I have experience with it, and I can say, well, I have an x and I have this, So in the end, I know when I chose this as u, I'm going to have a cancellation, and I'm going to get rid of that. If I were to choose some other u, it wouldn't have worked out. But anyway, proceeding along, we had an integral in terms of u, and we just simply integrated it. We turned it into a form that we knew how to solve from the previous section. So we integrated it. We had a function of u as our answer with a constant, and then we just simply took our u that we picked and we plugged it right back in so that it's all self-consistent, and that's the answer to the problem. And that, my friends, is one of the most powerful techniques in calculus that you're going to learn. Okay? Integration by substitution. It's going to take up a significant fraction of your class. It's going to take a significant fraction of your test. It's going to be very important as you go on past calculus to other sections of math. It's very, very, very important. And the big mathematicians get paid big bucks to figure out how to do substitution right. What if you have integration of sine of 4x dx? Well, you might look at that and you might say, well, geez, I know how to integrate that. He already told me what the integral of the sine was. And you're right, I did tell you that what the integral of sine was. But that was the integral of sine of x. Okay, here you have the integral of sine of 4x. That's different. You can't just simply look at similarity there and figure it out. I've given you a list of integrals of very specific things, and you have to only use those things. So we need to transform this into a form that we know how to solve. And so again, from experience, and you'll gain this experience as we go, I'm going to set u is equal to 4x, like this. It's going to be my u. Immediately when you put that u down, you say, okay, du dx, the derivative of u with respect to x is, and you take the derivative of this, which is simply 4, and you should be comfortable taking derivatives now, so that's the derivative of that. And so to continue on, du is equal to 4 dx, and just move the dx over, and then so simply dx is 1/4 du. So that's solve for dx. Now, you don't have to do this in every single problem you solve, but because we're new at this, this is the important piece of information that we've derived, and this is the important piece of information that we've derived. Those two things are going to be the things that allow you to write this integral in a form that you know how to solve. So, what you'll have is the sine of what? Of u. Because 4x is u, and we got to plug in for this. So dx is just simply 1/4 du. Now this looks real nice. I can take the constant out of the integral just like we know we can do, and you have the integral of sine u du. Now, you know how to integrate sine u du because I told you that in the previous section of the class, and that is equal to negative cosine of u. Obviously, you've got to add your constant on like you have to do for all of these things. So, it's negative 1/4 cosine u plus a constant. And you don't want to leave your answer in terms of u. You want to plug your answer in. U is equal to 4x, like this. And this is your answer. So you see, it's pretty close to what you would guess by thinking that you can just sort of do it directly, but you have to go through the motions of defining u, taking the derivative, finding dx, plugging it in. Notice that after we made the substitution, I turned the integral into an integral that I knew how to solve. Sine of u du is cosine u, and so then I just plugged back in for u, and that was it. This is the mechanics of how to do it. You just plug in your value of u, you plug in your value of dx, and hopefully you've simplified it. Now, this is going to be a pretty lengthy section. We're going to work a lot of different problems because, like I said, you're only going to learn how to do this by examples. So we're going to work examples. So if you want to pause the video anytime here after I write the problem on the board and try to work it out yourself, that's a really good idea. And then you can just compare it with my solution. If you get stuck, it's great. You can just press play, and then you can see where you went wrong. So here's my integral, and I'm going to put my u over here. Again, this is from experience. I'm going to pick x squared plus 6x. And I'm going to show you why I picked that in a second. Of course, I've already worked these problems out. Du dx, the derivative of u with respect to x is 2x plus 6. 2x here, and then plus 6 here. And I'm assuming that you know how to take the derivative now because we've practiced that. Okay. And also further note that this is just simply du dx. This is just simply, you can factor out a 2 and you get x plus 3. You see the x plus 3 here that shows up here in this derivative? You see the x plus 3 that shows up here? That is how I knew to choose this as my u. Basically, when you pick a u, you're going to end up taking the derivative of it. And when you end up taking the derivative, it's going to end up going on the bottom. And you just want to pick something that when you do that ends up canceling with whatever's left over in the problem here. And as you work problems, you'll get experience with that and see that that happens. So solving for du is just simply 2 times 2 plus 3 times dx. I just moved the dx over. And then the dx is just simply 1 over 2 parentheses x plus 3 times du. I just solved for dx there. Now you see how this is going to end up canceling with that? It's beautiful there. That's exactly what you want to see. If you start picking a u and taking a derivative and you see nothing's going to cancel, well then you might as well stop. You've done the wrong thing. So I have x plus 3 on the top. I have u squared on the bottom because this is u, and don't forget that it's squared, times dx is just simply what I found here, which is 1 over 2 parentheses x plus 3. And then don't forget that you got a du here. Now you see this is where the rubber meets the road. This is what makes this problem work. Because I have done this, and because don't forget there's an implied parentheses around this, this cancels with this. Now there's no more x's in the problem. Prior to that point, x's were sitting there with your u's and then you can't do anything further, but since the x's cancel, that's perfect. Now you'll have 1/2, the 1/2 can come out of the integral 1 over u squared du, right? And you know how to solve this. We can turn this into a u to the negative 2. We did a lot of problems on how to do that in the previous section. We just moved it up, and now this is a polynomial. So this integral is equal to 1/2, which is what's out front, divided by exponent plus 1. So you're going to have a negative 1. Negative 2 plus 1 is negative 1. And I made my fraction a little bit too big here. Okay, times u to the negative 1. Again, negative 2 plus 1 gives me negative 1. And don't forget that it's plus a constant. So when you do some simplification here, you're just going to have a negative sign come out, negative 1/2. Okay, times, and then this u to the negative 1 means I can just put u in the bottom, because u to the negative 1 means I can just put that u down there at the bottom, plus a constant. Now you don't want to leave your answer in terms of u, so you just leave it in terms of this. Now don't forget u is defined by this up here, so I'm going to put that right here, x squared plus 6x right there, plus a constant. You see? So it's not really bad. And of course it's going to seem very easy because I'm doing the problems for you, but really the trick is obviously being good with your math so you don't screw up a sign error, but really it's defining what u is. It's figuring out what to do for that substitution, and that takes practice. That really does. Usually when you notice, you'll see these problems, they're all set up to have some kind of cancellation, and they're doing that on purpose so that they can get the problem where you can solve it. Now what if you had the integral of 2x plus 1 times x squared plus x plus 1 all cubed dx? Okay? Well, you're going to start to wonder, what can I choose for u? And I can just tell you from experience, you're probably going to be thinking, should I choose this for u, or should I choose this for u? Now, there's other ideas you could do, but generally, that's going to be your first thoughts. Okay? Now, let's think about it. If I choose this for u, when I take the derivative, it's going to be 2. The derivative of this is 2, which is not going to cancel with this at all. But if I take a look at this and I say, what's the derivative of this? This will be 2x plus 1. The derivative of this term is 2x plus 1. if you think about it, which sure looks a whole lot like that, right? So that may lead me somewhere. So let's try it. U is equal to x squared plus x plus 1. Du dx is equal to 2x plus 1. 2 comes down, x to the 1 power plus, and then you've got your coefficient in front of x there is just a 1. And if you're confused about how to take any of these derivatives, go back to the section of this very DVD on how to take derivatives, and this is done over and over and over again. Okay? So then du is equal to 2x plus 1 times dx. I'm going to put some parentheses here to make it clear, right? I just moved the dx over by multiplying. And so then dx is equal to 1 over 2x plus 1 times du. And I just divided both sides by 2x plus 1. So now, having this piece of information and this piece of information, I'm going to go back and I'm going to try to solve this integral. So I'm going to have 2x plus 1 times u to the third power, because all of this is just u, to the third power, times dx, which I've defined right here, 1 over 2x plus 1 times du. And this is sort of what we predicted would happen. This term cancels with this term, which is exactly what we wanted. We want to get rid of all these x's. So in the end, it's a very simple integral, u to the third power du. And you already know how to solve that, right? We've been doing that a lot. So we'll have 1/4, 3 plus 1 is 4, u to the 4th power, because 3 plus 1 is 4, plus a constant, right? And we don't want to leave our answer in terms of u, so u is equal to this. So what I'll have is x squared plus x plus 1 to the 4th power plus c. And that should be my answer. You see what I'm saying here? There's not many steps. I mean, geez, sometimes in Algebra 1, solving an equation or a system of equations can take more steps than that. This is calculus, you see? That's why I was telling you in the beginning. It's not terribly hard. It's just that you got to practice it to figure out what to do. The steps here, there aren't that many of them, and there's not too many rules either to remember. You just have to practice them. You know, when you were a little kid, adding two numbers together seemed really hard because you had never seen it before. Same thing with this stuff. It seems very hard, but that's just because you haven't seen it before. So what if you have the integral of the square root of x minus 1? You don't know how to integrate that. Of course, you got to have a dx, right? Otherwise, it's not a valid integral. You don't know how to integrate that because I haven't shown you how to integrate that. So we're going to transform it. Really, the only thing to pick here for your u is going to be x minus 1. There's not too many choices here, okay? So then du, dx, the derivative of u with respect to x, is equal to 1, because the derivative of this is just 1. So then du is equal to multiply by dx, dx. This is very simple. Du is equal to dx. I don't have to really do anything else. So I can rewrite this integral as u to the 1/2. This is u. It's a square root, so I'm just writing it as 1/2 times du. Because dx is equal to du, so I just write the du. You see how simple that becomes now? And then in order to integrate this, we're going to do it just like we've been doing any kind of these polynomials. 1 over the exponent plus 1. 1/2 plus 1 is 3/2. U to the exponent plus 1 is 3/2. And then you have to add your constant, which you always have to do. Now 1 over 3/2 is just 2/3. You just flip the fraction over, multiply, so you get 2/3. U to the 3/2, well, u is equal to this, so I'm just going to say u is equal to x minus 1 to the 3/2 plus c. That's the answer. That's the answer. So you start out with something really foreign that you don't know how to do at all, and you end up beating it into a form that you know how to do. And in fact, all of the problems we've done so far have been just finding a substitution that turns it into a polynomial of some kind. This problem next is going to be a little bit more challenging, not terribly more, but a little bit. What if you have this, x plus 2, and on the bottom you have a 1 raised to the power of 1/4 dx. Okay. This one is an example of when you have to do a little bit more trickery here, okay? You have to work with me, and I'll show you what I'm talking about. We're going to say, just like we have always been saying, x plus 2, u is equal to x plus 2 is my first guess. So then du dx is equal to 1, right? The derivative of this quantity is just simply 1. And so then du is equal to dx. Very simple so far. Right? Let's go ahead and try to rewrite this integral. And I'm going to do it over here next to it. I'm going to say the integral of x over u is x plus 2, so I'm going to have u to the 1/4 power, like this. And then dx. dx is here, so I'm going to put du. Now, we've run into a problem, you see. The reason we have a problem here is because I've done my substitution. I've done my substitution for dx and also for this. And in the end, I still have x here, and I have a u, and I cannot integrate that function. In all of the problems up until now, when we've done our substitution, we were able to cancel some x's somewhere, and then we're left with a function of u, and I can integrate that. Here, after we've done the substitution, you can't do that. Now, normally what this would mean is you would go back and try to find another u, and maybe you guys are smart enough to do that. I couldn't find another u that would help much. Okay, but there is something you can do, obviously, or otherwise I wouldn't have shown you this problem. As we said, this is an important piece of information. This is an important piece of information. Take this and solve for x for me. X is going to be u minus 2, right? X, I'm going to subtract 2, so you get u minus 2. Okay? You get u minus 2. So I'm going to work with this, which is what I've been working with, and I'm going to say x is equal to u minus 2 over u to the 1/4, and I'm going to integrate that du. Now you see I have a function in terms of u. So here I did a substitution and I had an x left over. Well, then I simply just turned around and used this definition to put it in terms of u. And now I have, in principle, a very solvable problem because I have an integral of u over du, but it still looks a little bit funny because I don't think I've ever shown you how to do something quite like this. So what would you do? This goes back to playing with the problem until you get it into a form that you can work with. So let's do that. This can be written as, this is two things on the top subtracted, and you got something on the bottom, right? This can be written as u over u to the 1/4 minus 2 over u to the 1/4. Obviously, all this stuff's over du. And you can convince yourself of that because this is two fractions, the same denominator. So if you were to subtract them, the denominator would stay the same, the numerators would be subtracted. So all I did was split this fraction up into two fractions. Okay? And you say, well, that doesn't look so much easier to solve. Well, when you have a u, this is u raised to the first power divided by u to the 1/4. This is from algebra. How do you simplify that fraction? Well, you subtract the exponents. So what you're going to have here is u to the 1 minus 1/4, which is 3/4. If you're having trouble remembering that, you can go review some algebra or pick up my video on algebra, and you'll learn how to simplify fractions with exponents like this. So you just basically, when you have an exponent on the top and an exponent on the bottom, you subtract the exponents as long as the basis is the same. In this case, it's u. So you can do that. So 1 minus 1/4 is 3/4. Okay? And then what you'll have here is minus 2 that comes from here, and I'm going to write this as u to the negative 1/4. And all I did here was I had the negative sign carried from here, the 2 comes from the top, and I'm just moving this up to the top, to the negative 1/4 power, like this. Now look at what I have here. I have a polynomial. Something raised to a power, something raised to a power, and I know how to integrate that. Okay? For the first term, it's going to be 1 over 3/4 plus 1, right? 3/4 plus 1 is 7/4. I think you can convince yourself of that. You could do that on a piece of paper somewhere. 3/4 plus 1, we could just do it here. 3/4 plus 1 is equal to 3/4 plus 4 over 4, right? And just change this to 4 over 4 to get a common denominator, and that's 7/4. Okay? So I have a 7/4 there, times u to the same thing, 7/4, because of this plus 1, minus, we've got to integrate this, 2 over 1 plus a negative 1/4 is just a positive 3/4, right? If I take this, negative 1/4, and add 1 to it, I'm just going to get a positive 3/4 times u, again, to the positive 3/4. And then don't forget your constant. When I integrate stuff, I have to have a constant. So just taking it one step further, you're going to have 4/7, because you just flip it over. 1 over a fraction, you flip it over. U to the 7/4 minus, and then what you have when you flip this over and multiply is you're going to have 2 times 4 is 8/3 u to the 3/4 plus a constant. If you're having problems manipulating these fractions, go pick up my video on fractions and it'll be good to go. Okay? And then, the only thing I need to do at this point is just plug in for u, and then I'm done. So I've got 4/7 x plus 2 to the 7/4 minus 8/3 x plus 2 to the 3/4 plus a constant. Now, we got the right answer there. And notice that this was a little bit more complicated than the previous problem. I'm trying to get a little bit more challenging as we go. We did a substitution, but in the end, we didn't get it totally in terms of u, but it's simple enough where we could just solve for x and get the whole things in terms of u. And you know, you could even look in a table of integrals at this point in the back of your book. If you find an integral that looks like this, you could just use it, but I just showed you how to split it up into something manageable, and you basically beat it into a shape that you know how to solve. And when you do that, you integrate it, plug in for x, and you get the answer. It's all about what you choose for your substitution and having that experience to know what to do next. Okay? Now let's do something a little bit different. We've been doing problems of a very similar type. Let's say we have the integral of sine cubed x. Remember that sine x cubed, that's what that means, times cosine of x dx. Okay? And why do we do that? Well, you're going to, obviously you don't know how to solve this problem because I told you how to integrate sines and cosines and stuff, but I never told you how to integrate sine cubed times cosine. So you have to pick something. So let's start out with u is equal to sine of x. Now notice right off the bat, I know I'm going to take a derivative of this, which is going to end up canceling with this because the derivative of sine is cosine. It's going to cancel, right? So let's show that. Du dx is equal to cosine of x, like this. So then du is equal to cosine of x dx by multiplying through by dx. And so then dx is 1 over cosine of x times du, right? Same steps we did for every single problem. We just defined u and we went from there. So then the next step of the problem is to substitute. U is sine of x. It's raised to the third power, so it's u cubed, right? Times cosine of x from here, times dx. But dx I've already defined as 1 over cosine of x times du. And then that, fortunately, gets me to cancel this, which I've already told you, if you start canceling things, you've generally done a good deed, and now you're left with something very manageable, u cubed du, which you know how to integrate. So how do you integrate this? It's 1, exponent plus 1 is 4th, u to the 4th plus a constant. And so then what you'll end up having is 1/4 sine x to the 4th power plus a constant. Okay? Not so bad. Okay? Now, I want to do at least one definite integral because we've already learned the fundamental theorem of calculus and how you deal with those definite integrals. And so I want to do at least one problem on that. So let's do something we haven't done before. And we'll do a trigonometric integral integrated from 0 to pi over 3. And what we're integrating is the sine of theta over the cosine squared of theta d theta. So sine theta over cosine squared theta d theta. Okay, this problem is no different than the ones before. I mean, you just need to pick a u and use the substitution and everything else. It's just in the end, when you solve the problem, you got this definite integral that you're going to have to deal with, and we've done a little bit of that already. So let's pick u is equal to cosine theta. Okay, notice when I take a derivative of this, it's going to end up being a sine function, and I think that that might cancel with this, so that's cool. So then du d theta, because that's the variable over here, the derivative of cosine is negative sine of theta, right? So then du is equal to negative sine of theta d theta. And then solving for d theta, because don't forget this integral is over theta, is negative 1 over sine of theta du. Like that. Again, it's the same old thing. We're just solving for one variable in terms of another. So then when you do the substitution, what you're going to have is integral from 0 to pi over 3. Okay, and what we're going to end up doing here is I'm going to say I'm going to have a sine of theta on top. On the bottom, I'm going to have u squared, because I have cosine theta squared, u squared, times d theta. But the d theta I've defined right here, so I'm going to have negative 1 over sine of theta here times du. And you know you've done a good deed, because when you do this substitution, this stuff cancels. Of course, I've got a negative sign that it didn't cancel, but the main thing canceled, and that's the most important thing. Now, I'm going to leave the limits out of it for a minute, but we're going to end up going back in just a second. Negative 1 over u squared du. Okay? Now, I need to write these limits down. Now, what I want to do at this point is remind you that when you integrate from 0 to pi over 3 in the original problem, this is from theta is equal to 0 to theta is equal to pi by 3. That's what you're doing, because these integral limits, these are in terms of theta, just like this is in terms of theta and this is in terms of d theta. Everything's in terms of the same variable, so this is theta. But you see, you have a problem here, because now you've got an integral over u, but your limits are in terms of theta. And that can't work out. In order for you to do this definite integral, you've got to change the limits to be in terms of u, just like you changed the body to be in terms of u. So it's very simple to do, though. You've got a formula for u in terms of cosine. So what you'll say is u is equal to cosine of 0. U is equal to cosine theta. Theta is equal to 0, so I've got u is equal to cosine 0. And then u is equal to cosine of pi over 3, okay? And then in the integrand, I'm going to keep it, I'm not going to do anything, but I'm going to write it as u to the negative 2 du. I'm just changing this fraction into an exponent. That's all I'm doing. Now, remember from your trig, cosine of 0 is 1, right? Okay, I'm going to have a 1 on the bottom. Actually, I'm going to make it even more explicit than that. I'm going to have a u is equal to 1 on the bottom. And on the top, cosine of pi over 3 is like cosine of 60 degrees, right? So then this is going to be like u is equal to 1/2. Cosine of pi over 3 is 1/2. You can use your calculator or your trig table to figure that out. And in the end, what I'm integrating is negative u to the negative 2 du. Now this is perfect. I've got an integral in terms of u, du, and my limits of integration are also in terms of u. And all I did was use this definition that I made to make that happen. So when you actually integrate this, what you'll have is negative, because you've got a negative sign, 1 over the exponent plus 1, negative 2 plus 1 is negative 1, times u. Again, to the exponent plus 1 gives me, again, a negative 1. Negative 2 plus 1 gives me a negative 1. like this. And don't forget that you're evaluating from limits u is equal to 1 to u is equal to 1/2. Okay? And so in the end, these negatives are going to cancel. They're going to make a positive. So you're going to have u to the negative 1, which at this point I'm going to write as 1 over u, integrated from u is equal to 1 to u is equal to 1/2. And so don't forget the fundamental theorem of calculus, which says that when you want to do a definite integral, you go ahead and you integrate it, but then you evaluate it at the top limit and then subtract evaluating it at the bottom limit. So what you will have is this evaluated at the top, 1 over 1/2. 1 over u is 1/2, minus 1 over, and then u is equal to 1. So I'm going to have this, right? And then so over here, this is going to be 2, 1 over 1/2. You flip it over. It's going to be 2 minus 1. This is just going to be 1. And so in the end, the answer is a big fat 1. It's amazing how much work you have to do to get an answer like 1. And you're going to find that all through calculus. A lot of problems end up becoming 1 or 0 or pi or something really simple like that. But one thing I want to point out before we close for this section is that when you have a definite integral, you do the problem the same way. You define a u, you take a derivative, you define your other variable in terms of du, so that when you write your integral down, it's going to be in terms of u, right? But don't forget your limits. Your limits are in terms of the old variable. So you've got to convert your old variable here, okay, and get your limits in terms of the new variable. And that's why I wrote it as u equals 1 and u equals 1/2 to remind me, yes, I'm in the new variables. And then you do the integration, okay, which we did by using the same method that we've always been using. This is the answer, but it's evaluated again at these new limits, and then you use that fundamental theorem of calculus to go ahead and figure out what the answer is. Final thing I'd like to say is, don't forget what integrals represent. Big picture. They're antiderivatives, right? But they're also the area under a curve between 2 points. In this case, it's the area underneath this curve between 0 and pi over 3. It's a physical area, okay? And when you do a substitution like this, what you're saying is that this integral, which has some answer to it called an area, is exactly the same area as represented by this integral here, which looks totally different. You've got a u to the negative 2, and then totally different limits. But these integrals are exactly the same. They give you the same answer, okay? And that's why substitution works. This integral looks different than this one, but this gives you the same answer. And since you're interested in the answer, that's why these tricks help you out.